In today's video, let's talk about the linear expected running time of the randomized select algorithm, and I will explain why it is effective on average, despite the worst-case quadratic time complexity. So the key to understand the linear expected time of the randomized select lies in the way the pivot is chosen. So we just assume the pivot tends to split the array into parts where each part contains the substantial portion of the elements, which significant process is made in each recursive step. Let's set up an example. Suppose we have the array A is contained the elements 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, and 5. And our goal is to find the median, which is the sixth smallest element, by using the randomized select algorithm. So assume that the pivot we chosen randomly is close to the median. So let's say we pick up 5 for simplicity, and then we do the partitioning. The elements are partitioned such that element less than 5 are on the one side, which is 3, 1, 4, 1, 2, 3, and the elements greater than 5 on the other side, which is 5, 5, 9, and 6. Since we are looking for the sixth smallest, and our pivot is at the seventh smallest in this arrangement, we are focused on the left subarray of 6 elements. We just recursively call it. The expected reduction in the problem size is by choosing a pivot in the middle half, which is between the 25th and 75 percentiles. At least 1/4 of these elements are effectively discarded in the future recursive call. Because of this, the maximum remaining elements in consideration after partition will likely be 3/4 of this original size n. Let's talk about the expected running time. So theta of n terms represent the partitioning cost, and the recurrence leads to the recurrence relation, which is T of n equals T of 3n over 4 plus theta of n, which according to the master theorem case 3, this recurrence T of n equals T of 3n over 4 plus theta of n, which can be solved to T of n is equals theta of n in expectation. So why is this linear? This algorithm expects the pivot to constantly reduce the size of this problem by at least 1/4 each time. So in terms of this number of elements left to sort, which is n, 3n over 4, and 3/4 squared times n, and so on. So this constant reduction by the fraction smaller than 1 leads to a geometric progression. So the sum of such geometric series, where each term involves a linear amount of work theta of n, adds up to a linear amount of total work. So in summary, while the worst case scenario occurs if the pivot is constantly the smallest or the largest element left, which causing quadratic complexity. So this randomized pivot choice typically avoid this scenario, right? Just by often choosing a pivot that partitions the array into substantially unequal parts. So this algorithm is more effectively reduces the problem size, which leading to a much faster average running time. So this is the essence of the middle half strategy and its impact on the efficiency of the randomized select algorithm.